Hello, Knox County Schools 7th graders. My name is Gary Petco, your kindergarten through 12th grade mathematics supervisor, and I'm here for week 3 of your KCS Safe at Home Mathematics Learning Packet. No, I don't come to you as Pythagoras this week. I just come to you as your plain old mathematics supervisor, because this week is going to be a little different. You notice in your packet you only have one page for math, and that page is a series of 5 problems, and that's intentional. Because this is part of our spiral review, spiraling back to earlier learning on topics that are crucial for the next week. And this topic is rewriting algebraic expressions in different forms. It'll set the groundwork for week 4 next week, which will be real crucial. So we go through and we'll be back to our 4 pages of math with problems, but again, we'll need today's topic to hit that. So let's review what we're going to do for that. We'll start off, introduce today's topic, as I mentioned. We'll work through each problem. Then we'll end with a weekly challenge and then remind you some extra available resources. And we got a couple of more on there for both the parents and the students that I think you'll like. Those 5 problems that you see in your packet revolve around the following standard. And the standard is labeled 7.ee.a.2. What does that mean? That just means this topic comes from 7th grade. The EE is expressions and equations. And A represents a cluster of standards and all grouped under the concept of the letter A. And this happens to be the second one inside that cluster. The standard reads, understand that the rewriting an expression in different forms in a contextual problem can provide multiple ways of interpreting the problem and how the quantities in it are related. Sounds like a lot of math jargon, but I think we can break that down. I've got the word expression in green because that's our key vocabulary that we'll hit on in just a minute. We're going to rewrite that expression different ways in a contextual problem. What does contextual problem mean? It has the word context in it. You put something in context, you're putting it in a manner that makes sense that you can use it. So put in a contextual problem. Some people used to think of this as real world problems or word problems. I don't like to say that because I think all math problems have words in them and all revolve around the real world. But put it in the context of an application of how you would use it out there in a job or in shopping. And another exciting part about today's topic is you'll be able to use this concept when you're working with your parents in shopping and with many other things today. What you're doing is it can provide multiple ways of interpreting the problem once you rewrite it, which is important because past couple of weeks we talked about fractions and decimals, how you can flow between the 2 different forms. Well, we're flowing here, but it's algebraic flowing called algebraic fluency. By rewriting the expression, you're building what we call algebraic fluency, being able to flow easily between concepts to have a better understanding so no matter what the problem is, you'll have an understanding of how to work it. So we can provide multiple ways of interpreting the problem and how the quantities in it are related. Algebraic expression, that comes from Module 6. An algebraic expression is a mathematical statement constructed from at least one variable and possibly one or more operation symbols and one or more numbers. Notice I've got the words variable, operation symbols, and numbers in different colors. So when you look at the 4 examples down there below it, you can relate. What you see in blue is the variables. What you see in green are the operation symbols. What you see in purple are the numbers. The variables are x's, y's, z's. It gets that name because a variable has a part of the word vary in it, meaning it could change. We put a variable in there because we don't really know what we're going to put in there. It could vary, it could change. And that's the fun of an algebraic expression. When we think of an expression in everyday context, an expression would be it's raining cats and dogs. That doesn't mean it really is raining cats and dogs. That's just an expression we use to represent what is really happening. Well, an algebraic expression is similar. We rewrite it in the form of variables to represent another thing that we're trying to interpret. Operation symbols. We've got the subtraction in green, the addition, and that little 2. Remember, that's an exponent, and that is an operation. That is something that changes numbers we operate on. And then our numbers are in purple. A reminder, if the numbers are in front of the variables, like the -2 and the 3, those are considered coefficients. If the numbers are standing alone, then they represent what we call constants. Right. As I mentioned, you've got a series of 5 problems, A, B, C, and D. All are different problems but revolve around this same standard. We'll work through each one. At this point, you might want to stop the video and start working some of the problems. Notice the answers are at the bottom of each problem, and that's okay, because that might help you jog your memory. But the solutions are not. So if you want to stop the video now and work a few of the problems, and then restart it, and you'll see how each problem has worked. All right? Okay, let's go with the first one. Problem A. Fred buys flags from manufacturer for $F each, and then sells the flags in the store for a 26% markup. See, there's where our context is. This is actual something that would be done out there when you start to get a job or when you're working at the grocery stores. Write an expression for the retail price of a flag, and then what is the retail price of a flag for which Fred paid $40? So let's break that problem down. That's what I love to do. Fred buys flags for a manufacturer for $F. We make that a variable F because we don't know how much he buys it for. Depends on the manufacturer. One manufacturer, one person, he might buy them for $40. One he might buy them for $30. It could vary. So therefore we'll make it the letter F. That he sells the flags in the store for 26% markup. Now keep in mind, if you have a business, if you buy something from somebody and then you want to resell it, you want to sell it for more. So that way you make a little money off of it. Selling it for more is called the markup. How much more? Well, that depends. Fred decides to sell his flags for 26% markup, which means 26% of the amount he bought it for. So if he bought it for $F, 26% of that is how much more he's going to make. We want to write the expression for the retail price. The retail price will be how much he'll sell it for at his store. And then part B is what is the retail price of the flag if he just happens to pay $40. So let's work through that problem. Oh, as a reminder, I'm going to pause this real quick. I'm going to tell you right ahead of time, I hold my pencil funny. Every teacher since first grade has told me that. It's just how I hold my pencil, and you'll notice that here. It's kind of funny, but it's just let you know it's going to be hard to see what I write at first, but I'll try to pull away so you see that. Got to get that out there first. Okay, Fred buys from a manufacturer. Now what I do is I underline and circle key things in a problem. That keeps me organized. He buys the flags for $F. He sells them for 26%. Selling the flags is what I said earlier was the retail price. We're going to call that the letter R just because we want to abbreviate it. It's the retail price, letter R. Now, as a reminder, this 26% from earlier work, 26%, that's a fancy way to say something, but we want to use math behind that, so we want to turn it into a decimal number. So as a reminder, 26%, 26 per 100% is 26 hundredths. The markup is how much money we're going to make. In other words, 26% of the amount he bought it for. Of is multiplies, 26% of F. That's 2600 times F will give us the amount of the markup in addition to what he bought it for. Okay, so the retail price is going to be F, how much he buys it, plus the amount he chooses to add on to it as a markup. That's what we've got to find. So an expression to write is F plus that markup amount, which is 26 hundredths of F. Now what we have as a reminder, that's two variables, and we can combine the like terms. Keep in mind in front of that F, if you don't see it, that's an understood one F, like F. So if we add those, combine those like terms together, 1F plus 26 hundredths F is 1.26 F. That's the expression that I've got circled for the retail price. Now, how would we use that for part B? Let's say he paid $40 for F. So if F happens to be $40, what would R be? What would the retail price? Well, now because we have that algebraic expression, we now can use that to find the answer for Fred, no matter how much he buys it for. So we just substitute the number 40 in there for F into our expression. So 1 in 26 hundredths, or 1.26, times 40. If we do the math behind that, that becomes 40.4 or 50.4 or 50 and 4/10. Within contextual results, that's $50.40. That's what his retail price would be. He would have that in addition to what he bought it for. So he bought it for $40. He sells it for $50.40, which means he makes $10.40 profit. Understood? Okay, let's go to the second problem. Jordan's dog weighs P pounds. We don't know how much, so we're just going to say P. Now, Emmett, his friend's dog, weighs 25% more than Jordan's dog. So we've still got this concept of more, and we got a percent. So you're going to start to see, hopefully, contextual how this is going to be used more and more. Now, what we want to know is which expressions, notice I got S, expressions, represent the weight in pounds of Emmett's dog. Not Jordan's, but Emmett's, because we already know what Jordan's is. Jordan's is P pounds. But Emmett's is a little bit more than that. It's 25% more. Select each correct answer. So we've got 5 choices. Let's see how many could be an expression we can use to find out what Emmett's dog is. All right. So what I'm going to do is I'm going to try to look at the problem and try to write what I think the expression is for Emmett's dog, and then see how many of those could be represented in the choices we have. Once again, I go through and I circle the key parts. I got Jordan's dog, which I think of as the letter J, abbreviated. Let's see, P pounds. We've got Emmett's, which we're going to call the letter E. And it weighs 25% more than. More than. Now, which expressions? I mean, more could be more than one. Okay, as a reminder, 25% is 25 hundredths, written as a decimal. Now, the words more than, as a reminder from 6th grade and early 7th grade, what does that mean? More than means to add on to it. It's more than Jordan's dog. So, we've got Emmett's dog is 25% of the weight of Jordan's. And just like in the earlier problem, of meant multiply. So we've got Jordan's dog plus, it's a little bit more. How much more? 25% of Jordan's dog, 25% of P. E equals P plus 0.25P. Now, as a reminder, that's an understood 1, so it's 1P plus 0.25P, or 25 hundredths P. Combining like terms, just like we did in the first problem, adding that 1 and that 25 hundredths, and I get 1.25P. Now, out of those 3 different ways I wrote that, which ones do you see in your answer choices? We've got choice E is in there, and it looks like we've got choice B. Both of those, when simplified or rewritten, represent the same expression. So E and B are our choices. Either one of those would work. Which one is better? I kind of like B myself because that gets me quicker to the answer. E works, but E is almost like a 2-step. I've got to figure out the weight of Jordan's dog. I've got to figure out the amount more and then add those 2 together. That would work, but if I understood how it works, if I understand B, then I can do all that in one problem rather than adding the amount onto it. I get it in the final answer. And we'll see that again here in just a minute. Okay, let's see what problem C is. Problem C, Anna. Anna needs to find the height of a triangle. She already knows the area of the triangle. She knows that the formula for finding the area of a triangle is 1/2 the base times the height. The area equals 1/2 times the base times the height. What your goal is to write an equation that shows how to rewrite the formula to help her find the height of the triangle. Remember, part of that original standard was rewriting expressions, rewriting equations. So what we want to know is, how could we rewrite this to find the height of the triangle? So I can take this formula and basically write it not as A equals, but as H equals. So if I know the area, could I determine the height? Sometimes we got to work backwards, and this formula will help us teach us how to work backwards. Okay, so let's see how this works. I'm going to go through and read the problem. I'm going to underline, I'm going to mark things. I know got the height, which is the letter H. She knows the area, which is what we abbreviate with the letter A. And she has that formula, 1/2 base times height. Now what I like to do is I like to write the formula down because I know I'm going to have to rewrite it in the terms of the letter H or in terms of the height. So what I really need to do is I need to write that formula down. I'm going to isolate that letter H. In other words, get it by itself. Have it as H equals, not with the 1/2, not with the B on it. So ultimately, I need to know what is H equals. What I'm doing is I'm actually doing the order of operations backwards. I'm reversing the process. And that's what you learn when you're rewriting formulas. You learn to reverse the process. You ask what operations are being done to that letter H. Let's undo it. I like to first of all take care of any numbers that are associated with H and say what is that number doing to H? And here we have 1/2 times H. So to basically mathematically get rid of that 1/2, I multiply it by its reciprocal, 2/1. Now, I don't really get rid of it. I change it to an amount of 1, which effectively says 1 times a variable. I just need the variable by itself. But I got to multiply both sides by the 2/1. And you can see when I multiply both sides, the left side becomes 2a/1 because I multiply by 2/1. The right side, that 2/1 times 1/2, when I multiply those two reciprocals, the product is 1. So I could write that 1 in front of the b, but I don't really need to with math. It's understood it's there. So 2a equals bh. But now I've got to isolate by doing something with that b. Well, b is multiplying that times that h, so I need to divide it. I need to do the opposite. And when I divide it, divide both sides by b. The left side becomes 2a/b. And it appears on the right side it goes away. Once again, it doesn't really go away. Multiplying by b/b, those don't cancel, but that turns into b/b is just 1, because anything over itself is 1. So it's really 1h, but I don't need to write the 1 again because it's understood. So I've got 2a/b equals h. But just to make it pretty and just for my sake, I'm going to rewrite that formula so it's h equals rather than h on the right side. It means the same thing. I'm using the symmetric property of equality. Symmetric has the word symmetry in it, like a mirror. You see symmetry, you see the reverse. It's the same thing, just rewriting the different order. H equals 2a/b. Now I have a formula, so no matter what the area is, I can tell you what the height is as long as I know the area and the base. All right? Rewriting that expression in a different form. Okay, let's move along to problem D. Maria needs to determine the lengths of sides of a rectangle. She knows only the perimeter of the rectangle. She knows the formula for the perimeter, which is 2 times the length plus 2 times the width equals p. You learned that in elementary school. How can Maria rewrite the equation to help her find possible lengths and widths of any rectangle? So much like in problem C, we're taking a formula and rewriting it. So let's see how Maria is going to do this. Maria needs to determine the length of the sides of a rectangle. So we call it length L. She knows the perimeter, which we abbreviate with the letter P. And she knows a formula for the perimeter. How can she rewrite the equation to help her find possible lengths and widths? So we're actually going to have two answers here. One, where we've written this formula in terms of L, much like in the previous formula we wrote in terms of H. And then another one, how would we write in terms of W? So let's get started. We'll write the formula down. 2L plus 2W equals P. We're going to isolate that letter L. In other words, we wanted to end up saying L equals something, not P equals something. So just like before, we have to ask ourselves what's being done to the L. We're going to reverse the process. I want to get rid of those 2's, so to speak. So I'm going to divide everything by 2. And if I'm dividing that 2L by 2 in order just to get as an L, because that's what we want to isolate, I can't do just the 2L. I got to divide everything by 2. That's our properties of mathematics to remain equal. Everything has to be done the same way. Okay, when I do that, I end up with L plus W equals P over 2. But now, in order to still isolate, I've got to make sure that W is not on that left side. The way we do is it's being added on, so let's just subtract it off. We don't know what it is, but we can subtract it off. and it takes it away. So I've got L plus W minus W equals P over 2 minus W. When I subtract it off, the left side just ends up with an L. The right side is P over 2 minus W. And there I've written a formula in terms of L. I haven't changed the formula than just rewriting it. I still have the same variables in there. Now we're going to repeat the process to isolate W. We're going to rewrite the formula. Now I'll skip a step because we would do the exact same thing. We would divide by 2. But in this time I want to subtract the L from both sides because I want the W by itself. So when I subtract L from both sides, I end up with a W on the left side equals P over 2, or 1/2 P, minus L. So there I have two expressions, one written in terms of L, one written in terms of W. In other words, one to find the possible length and one for to find the possible width. Rewriting formulas. Sometimes we know the parameters. Sometimes we know the width, and we just need to know what is the length. This is now we've got a formula. I could have used the original formula and done that, but this kind of shortcuts it, so everything is already written in terms of L. Okay, moving on to our last problem. Which expression is equivalent to 6/10 times x, or 0.6x? We've got 4 different expressions. Now what I'm going to do is I'm going to simplify, if possible, all 4 of these expressions and see which one would actually simplify to 6/10 times x. And that's how I'm going to work this problem. So let's start this off. The first one, x minus 4/10 x. Which ones are equivalent? Equivalent means the word equal. Now, as a reminder, every time I just see a variable by itself and it looks like there's nothing in front of it, the coefficient is actually 1. So I'm going to rewrite that as 1x. Sorry, I think that's my dog barking in the background. 1x, take away 4/10 x. Since both those terms in the expression have the variable x, I can combine them by subtracting the coefficients. 1x, take away 4/10 x, becomes 6/10 x. Ooh, that looks like that evidently is equal to, because it simplifies to 0.6x. So yes, that one is equivalent. But this next one, if I rewrite that, since that 1 doesn't have a variable tagged with it, I can't combine a variable with just a constant. So that can't be simplified anymore. So in its simplest form, it's not equivalent to 6/10 x. So it's no. In a similar fashion, choice C, those two terms don't have an x, so they're not like terms. I can't combine them. That's as simple as it is. That's equivalent. That's my simplified expression, so no, it doesn't equal. The last one, those do have, each term does have an x in it. I can combine those, much like I did in part A, but when I start to combine those, 6/10, take away 1x, reminder of what it looks like from the previous weeks, add a negative, 6/10 plus a negative 1 gives me a negative 4/10 x. That does not simplify to 6/10 x. So it does not. So the only choice that's equivalent is choice A. All right. So we've gone through each one of the 4 problems, each one of the 5 problems, written the solutions. I hope that makes a little bit more sense as we go through these. Again, these are spiral reviews, revolve around rewriting expressions to build algebraic fluency. Hope this has helped you out. I hope you have a fun week. And as a reminder, here's some resources. We got a new resource. I should have reminded you last week. There's a great resource on PBS. If you're already looking at some of the videos on PBS, something called Mathline. Mathline is hosted by a great friend of mine, Artie Roberts, former teacher of mine, former colleague of mine, great teacher from Bearden High School. He's on every day, Monday through Friday from 6 to 6:30 on PBS, and it's a live call-in show, and I actually help him out some Mondays. You call in and you can ask him help on any math problem. You give him any one of these problems. You give him a problem you want to work on, and he'll work through it on live with you. It's a 30-minute show. The number is 844-686-2378. Give him a call Monday through Friday, 6 to 6:30. He's there to answer your question. Or you can connect with him on Facebook Facebook/Mathline Online. It's a great resource. Parents, a resource for you. I've got this on our Knox County Schools website, my math website, but here's some ways that you can help out. If you just want to do math in general, that's the fun part. There's so many ways we can do math. Math, you can look for shapes or patterns in life with your children. Have children measure ingredients when you're making a recipe. Ask your child to explain the math skills he or she is working on in these packets. Various different things. Look at that number 8. Real simple. When you're comparing things, which is tallest, brother or sister, the door or the counter? Trying to get students to understand and conceptualize the math in terms of lengths and quantities. Number 7, ask your child to count change at the grocery store or online nowadays as we're kind of at home. Number 10, encourage your child to track or graph scores from one of their favorite sports teams. So many ways to talk math. That's the fun part. Talking math is building math concepts. And once again, as a reminder, we've also got resources with this packet in addition to previous packets on our website, KCS Safe at Home. Folks, I hope you have a great week, and I look forward to seeing you next week. Thank you, and I'll talk to you later.